In the next couple of videos, we're going to investigate the behavior of our intrinsic semiconductors. And so up here at the top, I have this labeled as band gap and electron-hole pairs. So at the moment, I don't expect any of those words to really make sense, but we're going to explain what's going on here in this video and the next. So let's start by talking about what is going on with the semiconductor when it's at a temperature of 0 Kelvin. So of course, 0 Kelvin is absolute zero. So at absolute zero, all of our electrons are bound to their atoms. So all electrons are bound to atoms. And so what that means is even if we apply an electric field, so small electric fields are not going to result in any current. Of course, if we applied a large enough field, we could sort of rip these electrons off. But if we were just talking about small electric fields, we won't have any current. But of course, our devices are not going to be operating at absolute zero. So even for non-zero T, even if it's really cold, but not at absolute zero, our electrons and our atoms are going to be moving around. So if we were able to look at sort of a crystal lattice, we would see these things sort of vibrating in place. And so what we can say is for non-zero T, we're going to have some electron energy. And if that energy is large enough, the electron can break away from our atom. So again, hopefully this is all just sort of a refresher from chemistry and/or physics classes. But of course, if anything doesn't make sense or if you don't remember it, feel free to ask me more and I can sort of give some more background. So for non-zero temperature, the electrons and the atoms have some thermal energy. And so we'll talk about how to quantify that in a little bit as well. And so if we have enough energy, our electrons can break away. So with enough energy, electron can break away from whatever atom it was previously bonded to. Once it's broken away, it can then move through our silicon crystal lattice, again assuming we're still talking about our silicon. But of course the same principle applies to any type of semiconductor. So in general, we have two different ways that we can represent this. And we're going to look at one in this video, and we're going to look at a second in the next video. So two different ways to represent. And I should say there's two different ways that we're going to look at how to represent this. Of course, there are some more that we could do as well. So the first way is using our 2D bonding diagram. So this is sort of the same diagram that we saw in the previous video. I've just expanded it a little bit to include more silicon atoms. And again, of course, we could say this extends in these directions because we're assuming that we have a lot of these silicon atoms sort of combined. I've also sort of color-coded these electrons. Remember, each of these lines, these blue lines, indicates a valence electron. So I've color-coded those blue to hopefully help make that a little easier to keep track of. But, so let's say all of these, so we're at some temperature greater than 0. And what that means is that all of these electrons have some energy. So let's say, for instance, maybe this electron right here has enough energy to break away from this silicon lattice. So what that means is it's going to move from that location, and maybe it comes over here, and it's just going to be hanging out up here. So this is our electron. So let me do a different color, let's say pink. And so our electron has now jumped from here to over here. In doing so, what's going to happen is it's going to leave behind this area. So let me do a dashed line. So it's going to leave behind this area here, which is going to have a net positive charge. So if we think about this was balanced in terms of charge, and then we take away an electron, well, now we have a positively charged region, and that positively charged region is what we call a hole. So we can say when our electron leaves a bonding site, we have a positively charged hole left behind. So just sort of what I was saying earlier, so there is a net positive charge And so we call this a hole. So that's going to be an important term that we use a lot throughout this course. And so simplistically, we're going to treat this hole as just another charged particle. So treat our hole as charged particle with charge equal in magnitude and opposite in sign of our electron. And so the notation is a little bit different than what, I'm going to use something a little different than what's in the book. So our charge of a hole would be lowercase q is equal to 1.6 times 10 to the minus 19th coulombs. In your textbook, they use a lowercase e instead. So of course then our charge for the electron would just be the same but with a negative in front. And so this idea of having a hole can be a little bit confusing at first, and I know I was a little resistant to it when I first learned about it as well. You can kind of try to keep track of it and think of it as just electrons, but it turns out that the math and the modeling all becomes a whole lot easier when you just accept that we can treat this positive charge particle, or this positive net charge left behind by the electron leaving, as a positive charge particle called a hole. So one other thing to point out here is for our intrinsic semiconductor, our net charge is going to be 0 because every electron that moves is leaving behind a positive charge. So for our intrinsic semiconductor, the net charge is 0, and so the reason for that is because we have every electron leaves a hole. And so, as you might recognize from the title, we can then call this creation of an electron and a hole, we can call these electron-hole pairs. Because every time we're creating a free electron, we also create a hole, so we could call these two things here one electron-hole pair. So once we can pretty easily think about this excited electron as moving throughout the system once we apply a small electric field, but we can also talk about our hole moving about the system. And so that's a little bit more difficult to see, but what we could say is let's consider maybe there's another electron now that has enough energy to escape its bond. So let's say maybe this electron over here has enough energy to escape. So what can happen is this electron can move from here and it can come over here to the space that was left behind by this electron. And so what we have then is we would have a hole left where this electron was, and if that electron goes here, then of course it's going to fill the space that was previously filled by the other electron, and we're going to be going back to having two electrons here. And so of course we can think about that as our electron moving, but we could also think about it as our hole moving in the opposite direction. So a couple other examples of our hole movement is we could think about a carpenter's level. So here's sort of an image in case anybody's not familiar. But of course with a carpenter's level, we're tracking the movement of that bubble. But of course really the bubble is just the absence of liquid. So the same idea here with our holes and our electrons. So instead of saying our electrons are doing this, sometimes it's easier to say our holes are moving in this way. But either way, we can say we have our holes and electrons moving throughout this crystal lattice. So excited electrons and holes move through our crystal lattice. And so of course, anytime we have charge moving, that is a current. So charge movement is going to result in current. So of course, if we want to have any type of usable current and we want to have this in sort of a net current across the whole semiconductor, we're going to have to apply an electric field. Otherwise, we're going to have random movement in all directions and it's sort of just going to cancel out. But we're going to come back to that a little later on, and we're going to talk about how we can get current movement from these electron-hole pairs. But the next thing we're going to do is, in our next video, look at a different way that we can represent this excited electron and this electron-hole pair.